let me, I'll explain where we are sort of in the whole course. In the next maybe 2.5, 3 weeks, we're actually going to we build up and we're going from the bottom up to the top. So this will finish when you'll actually implement your own like solver for an LP solver or something like that. We haven't quite figured out, but it'll finish with you implementing like a solver. So you mostly, by the way, just to demystify it, right? Just so when someone looks at you sometime in the future and says, oh my God, you can't write your own LP solver. That's really complicated. And you could say, au contraire, I did it, right? So that's the main thing, the main reason. But also this interesting stuff. Right now we're at the bottom level, which is linear algebra. And actually, in some ways, it's by far the most important level. And my own feeling is everybody, certainly anybody in this class needs to know this material. Do you need to know a whole 10-week course, that you would take on computational linear algebra? Maybe, actually. But this certainly you need to be familiar with the ideas because, and that's unlike, you don't have to know about computer architecture, even though everything we do is thanks to the people who design and build, computers and stuff. So, but this you actually should know. Okay. So back to the numerical linear algebra. And today, actually, we're going to cover material that is like, some of you may know, the rest of you probably don't. And it is, I'd listed in the top 10 of the things you need to know from this course, even though it's not technically part of the course. So, okay. So here it is. Last time we talked about, how do you solve a set of equations AX equals B? And there are several ways. There's ones we're not going to talk about. There are iterative methods to do this, which are used for like super large scale problems. If you've got like a billion variables, or if that represents like a PDE you're solving, right? We're not going to talk about those. We're going to talk about, these are what are called direct methods. I don't know where that name came from, but they're called direct. And the way they work is they take the matrix A and they first factor it into a product of matrices, each of which, quote, is easy to invert, unquote. So that's the first step, right? You've seen some of these factorizations, like SVD, eigendecomposition. You've probably seen a couple of the others as well. So an easy to invert is actually just, that's dialect for it's easy to solve equations with that coefficient matrix. So that's what it really means, because no one is inverting anything, right? It is unbelievably rare in good numerical work for anybody to actually form the inverse of a matrix. There are cases where people do, but it's very rare, right? So, okay. So what you do then, once you've factored your matrix into a product of things which are, quote, easy to invert, unquote, you have to interpret that correctly, then what you do is you then write out, the inverse, and the inverse is the product, is the product of the inverses in reverse order. And then you literally just evaluate this by first evaluating, A1 inverse B. That's one thing. And of course, what that means is people write A1 inverse B. What they really mean is you call solve A1 comma B. That's what it really means. So you solve that. Then you pass this solution to the next thing, which is A2 inverse times X1. And so you solve A2 X2 equals X1. And that gives you the second one. And you keep going until you get to the end. So again, it's like completely straightforward, like, okay, like, so what? Last time we talked about some very interesting things, which is that if you want to solve a set of equations with the same coefficient matrix, but different right-hand sides, right? Then in fact, what you can do is you factor once and you cache the factorization. And then you simply use the solve method. This is called the solve. The first one is called factor, and this is called solve. And so you simply call the solve method on your multiple right-hand sides. So, and you get to some like stunning, you get to surprising conclusions in some cases. I'll get to that in a minute. So, all right. So this is the one that you probably saw a variation of this, like in high school or something. The first time you saw linear equations, it's called Gaussian elimination. It's called lots of things. But here's what it is. If you have a non-singular matrix, you can factor it as a permutation times a lower triangular matrix. It's a lower triangular and U is upper triangular, and they're all invertible. Of course, actually, if any one of them weren't, then A would not be, right? So the cost of that factorization, which we're not going to go into how that's done, it's actually not that difficult, but the cost is order n cubed flops, okay? So that's what that is. And so this is what it looks like to solve, linear equations. You factor A, that means you get P, L, and U. Then these three steps, like 2, 3, 4, this is factor, and then this is solve. So again, all you do is you just solve them in reverse order. Now, solving this one, solving the permutation, this is silly. It's just you multiply by P transpose, right? Roughly. Right? It's the inverse permutation. You just unpermute them, right? So this is easy. The second one, L is lower triangular. And so for that, you use forward substitution, which we saw as an order n squared algorithm. Backward substitution is when you have U, because U is upper triangular, and you start, if you will recall, by first solving for the last entry, then the second last, then the third last, and so on. That's backward substitution. And that's also n squared flops. And if you add these up, what you find out is something kind of weird. It's that the factor is order n cubed and the solve is order n squared. And so I think last time I finished by asking you a question, which is like, how long does it take to solve, I don't know, on my laptop, a set of linear equations with, let's say a 1,000 by 1,000 matrix, right? Which I could make sound pretty impressive, right? I could say, my problem has more than 1 million coefficients in it, which is true. 1,000 by 1,000 matrix does. And then you could say, the n cubed, the factorization is order n cubed. That's like 1 billion flops, right? Of course, that's a joke now, right? So, and the answer is like, I can do that in 100 milliseconds. Okay? So can you. My phone can do it in something on that order of magnitude, right? So, which is actually kind of stunning. I think then I asked the following question. I asked, how long does it take you, if it takes 100 milliseconds to solve, let's say, one set of 1,000 by 1,000 equations, right? 1,000 equations, 1,000 unknowns. How long does it take to solve 10? For that matter, even 100. How long does it take? If it takes 1/10 of a second to do one, and the answer is surprising. It's this. It's 1/10 of a second. Everybody got that? So not that many people appreciate this, right? Or understand this. And this is actually, this is used throughout a lot of numerical stuff. A lot of it, you use it all the time, you just don't know it. So all the solvers that you use when you call CVXPy, almost all of them, will use things like this, right? So the most typical methods to solve things like SOCPs, SDPs, these things, or for that matter, even LPs, involve two solves, right? And that's done in the same, basically the factorization dominates. And that's the point there. Okay, so, all right. Actually, I'm just curious, how many people have seen this before? How many people knew that you could solve 10 equations with 1,000 variables, 1,000 unknowns? Same coefficient matrix, different right-hand sides. You could do that. You could solve 10 in the amount of time it takes you to solve 1. You knew. Come on, say other people. Yeah, is no one else impressed, or like, shouldn't you be? I mean, maybe it's too early, but people should be going like, that's awesome. Like, really? But I'm not getting that feeling. But that's okay. That's fine. Okay, good. But there we go. All right. Now, sparse LU factorization. This is super interesting. This is something everybody should know about, right? So since, I guess it's been developed since about the 1960s, is basically stuff on sparse matrices, right? And so everything, first of all, what are the data structures used to store them? And then basically there's a whole parallel universe of doing all the stuff you would do with so-called dense matrices, which are just stored as arrays, right? How do you do this for sparse matrices, including factorizations, back solves, all these kinds of things, everything you can do, eigen decompositions, singular value decompositions. There's a whole field where people have made this efficient for sparse matrices, right? And this is something like everybody needs to know about, like everyone, because if you do any kind of computation, you need to know about this, right? Because there will be, again, there will be surprising statements we'll make about what you can solve and not solve. Okay. So if A is sparse, the typical factorization is going to have 4 factors. It's going to have a P1 is a permutation in front, P2 is a permutation in back, and then L and U are these are the lower triangular and upper triangular, and those. So the idea here is mathematically you don't need P2, right? You do need P1. It is false that any matrix, any non-singular matrix, can be factored as LU. Okay, you do need that initial permutation, but you don't need that second one. So the second one is there, and by the way, P1 is also there, so that when you carry out this LU factorization, L and U will also be sparse. Because if you do this, if you're not careful about doing this, your matrix A will be sparse, but L and U will be like dense. Okay? When that happens, it's referred to as you have fill-in, right? You have lots of entries in L and U that weren't there in A. Okay? So, and this is very important for everybody to know, right? So, and here would be an example. It's extremely common to work all the time with, let's say, a million by million sparse matrix. It is simply not a problem, right? I can do stuff like that on my laptop, right? The number of non-zeros is not going to be 10 to the 12, which would be a dense one. It's going to be something reasonable like, I don't know, it's got 50, 20, 30, 100 non-zeros per row. Even that is not that big a deal because it's 100 million, then it's 100 million coefficients if there's 100 non-zeros per row. And you multiply that by about 10. So even in doubles, it's like a gig, which is just like very small. It's a reasonably small amount of memory. Okay? So anyway, so what happens is if you have your million by million matrix and you call a solver like this, if you choose P1 and P2 poorly, then what will happen is like L will be like a dense lower triangular matrix, right? You can't even store it because it's a million by million, right? So it's 10 to the 12 divided by 2 things. I mean, you can't. Let's just leave it that way, okay? Making sense? So the P1 and P2, they're chosen heuristically, and you can, people have been doing this since the 60s. It's actually very cool. You can ask questions like, oh, find me the P1 and P2 that minimize the number of non-zeros in L and U. That's a perfectly nice problem to come up with, and it is NP hard. Okay, so but who cares? It's silly. There are unbelievably good heuristics for doing this, right? That all of us benefit from. So this is great. Okay, and so what happens with sparse matrices is the factor and solve times, whatever they are, they are less than 2/3 n cubed. And I'm gonna give you a very important special case right now, and then we'll encounter others, right? So here's a super important special case. It's a so-called banded matrix. So a banded matrix looks like this. Well, of course, there's just a band here, like this. Maybe this is k entries wide, right? And basically, this is non-zero, and everything out here that's 0 and that's 0. So that's a banded matrix, right? So I can store a banded matrix on my laptop easily if it's a million by million, and the bandwidth is, let's say, 10 or 20, right? So that's a banded matrix. No, that's fine. So it turns out when you this is a case where you don't need P1 and P2, right? But if you simply do the LU factorization here, the L and the U are going to be basically the same. They're also going to be banded. So I'll just write down L. L is lower triangular. So whoops, this goes down to there, right? And then it simply looks like that. That's k over 2. And this is what L looks like. And U looks similarly, right? So by the way, sometimes a banded matrix comes to you looking like that, but sometimes it's been permuted by whoever formed the problem, right? They decide, well, I'm going to list all my states first, then all my controls, then all this in an optimal control problem. And then they comes out with some crazy sparsity pattern. And any methods used to heuristically choose P1 and P2 will permute it to look banded. Okay, so what happens in a banded factorization is, first of all, the factorization time is nk squared, and then the back solve is nk. Okay, so these are stunningly smaller than n cubed, and n squared. Okay? So what this tells you is you can solve a million by million equations if the bandwidth is, 10, like super easily, and it's going to be so fast it's not even funny. Everybody following this? So, which is kind of shocking, right? Because someone said, what are you doing? You say, I'm solving a set of a million equations for a million variables. Each equation involves 10 of the variables. And you're like, whoa, that sounds like it's hard, right? The answer is, it's unbelievable. This is a millisecond operation. Everyone follow? This is completely insane. So, but this is things you absolutely need to know this, right? Because this is the trick to many, many things. Okay. So what's, by the way, what's interesting here is the factor solve ratio is not that high anymore. Now it's K. It used to be N. And so that says, if I say, how long does it take to solve a million by million equations banded with a bandwidth of 10? It's some number which is shockingly small. Then you say, how about 10 of them? Okay, how about 2 of them? And you say, it's only a little tiny bit more. Everybody following this? Okay, so by the way, what you'll be doing in the next week, 2 weeks, is you will start to recognize matrix structure like sparsity. You're going to see some others later today, like block arrow and weird other ones. We'll show, and you will start recognizing them. They're super important because 2 things. Number 1, you'll start recognizing structures that you can exploit to solve extremely fast. That's number 1. But number 2, on the other end, you're going to start recognizing practical problems that have that will result in matrices with that structure. I'm going to mention one right now. All of control, all of signal processing, just looks like that. Every last bit of it. Okay? So that means if I ask you to, you've solved problems, little control problems and things like that. But what this says is, if someone says I have to solve a control problem with, 20,000 time steps and a state dimension of 20 and 10 actuators, and someone say, wow, that sounds like it's going to be complicated, you just laugh and say, are you kidding? Like, I can do that on my phone. And of course, that's the key to, actually putting these things into a lot of control systems, right? So that a lot of them actually do this. So, okay, so that's the big picture. So this is just like super cool to know about. Okay, this brings us to the a very famous factorization. It's about 100 years old. It's the Cholesky factorization. So if you have a positive definite matrix, you can write it as just LL transpose. And if you insist that the diagonal entries of L are positive, then it's unique. So there's no choice. There's just one factorization, period. That's it. There's one way to write A as LL transpose. And how do you solve, how do you solve AX equals B, where A is positive definite? That's called a positive definite system of equations, right? So how do you do that? You do a Cholesky factorization, and you do a forward and a backward substitution with L and L transpose. Okay? So that's it. And, actually, it's 1/3 n cubed as opposed to 2n cubed for general matrices, and that kind of makes sense. I mean, first, number 1, no one cares about a factor of 2 in a flop count estimate because these are so crude. Right. What really matters is like the people who actually wrote the microcode and all that kind of stuff, and how's it blocked and how many cores is it using, all sorts of crazy stuff internal that we don't have to, most of us don't, all of us, I'm guessing, should not and do not have to worry about. Right. But we should also all be very grateful that there are people who do. Right. So, so there it's a factor of 2, which is not unsurprising. It's symmetric. So roughly speaking, there's a redundancy of 2. Or you can even look at this and say, hey, that's an LU factorization with U equals L. And why? You say, because the matrix is symmetric. That's why, right? So it's not, anyway, not too surprising. We will see very shortly where positive definite systems of equations arise. Right? Actually, they arise by themselves in a lot of applications, but specifically in convex optimization, we'll see they're at the heart of a lot of stuff. Okay? And now we get the sparse Cholesky factorization. And here I'll tell you something super interesting about it, I think. So here, it turns out, this is basically the same as calling a Cholesky factorization on P transpose AP. Right? Because take that equation, just multiply on the left by P transpose, on the right by P. So what it basically says is permute your matrix, your positive definite matrix, and then do a Cholesky factorization where there is no creativity. It's just there's a unique Cholesky factorization. Everybody got this? When you do that, you will find some stunning things out. You will find out that if you choose a good permutation, the L is going to be super sparse. If you choose a bad permutation, it's going to be dense. So, and I'll give you sort of a famous example of this. So it would be something like this. If I gave you this matrix here, so I'm going to draw a, here, I just make it this way. So it's got first row and column and a diagonal. Okay, so by the way, that's called like an up, what do they call it? It's an arrow matrix, right? Because if you blur your eyes, it looks like an arrow or something. I don't know. Anyway, that's an upper arrow matrix. Everybody got, it's super sparse, right? Number of non-zeros per row and column, except for the first row and column, it's like 2, right? So, okay, so that's an example of that is an example of a structure you should never ever see again and not have an emotional response to. Ever, right? Because this is super important. Okay, so, okay, if I do a Cholesky factorization on that, here's I'm going to show you the sparsity pattern of L. It's this. Ready? It's completely dense. There. Completely dense. Okay? So this, of course, ruins everything, right? For one thing, you can't even store that much, right? Because if you started with a million by million, upper arrow matrix called Cholesky on it, it would, at some point, your OS would say, no, I'm not going to allocate that amount of memory. No. So everybody got this? Okay. So now, turns out, all you need to do with this is permute the first and last columns, and first and last rows and columns, and then you end up with this matrix. And that's called like a, I don't know, it's a whatever. That's called an arrow structure, right? We'll get to others, but anyway, that's one. Okay, if I do a Cholesky factorization on this, I will show you the sparsity pattern you get. You get this, and that's all. Okay, so what it means is, if it means that the permutation that permuted this into this was super important, at least from a sparsity point of view. Okay, everybody got it? So what this means is if you had that set of equations to solve, actually, if you just called a sparse solver on your behalf, you wouldn't even know it, but the permutation would change it to this, factor that, and then your factor time is going to be order n, and your solve time will be order n. Right? So everybody following this? So that's it. So this is, now, fortunately for a lot of those things, you don't have to worry about it. That's all based inside. All of you have benefited from this probably 1,000,000 times just so far in this class. Because every time CVXPy calls a solver, this is what's happening. This is the kind of stuff that's happening on your behalf many, many times every time you call solve on something. Okay? So doesn't matter. I mean, but just now you know. Okay, does make sense? Yeah.
How much time does it take for the solver to find that P?
That's a perfect question. I should have said it. So the question is how long, so yeah, if I say, oh man, are you kidding? I can do this for you, not a problem. I'm going to find a permutation like that, and then I can solve this in a tenth of a second. And you go, cool. How long did it take you to find the permutation? You go, a couple days. It's just not, yeah. So the general rule of thumb is people use heuristics for finding P that are, they hope, on the order of magnitude of the amount of time it takes to actually do the numerical factorization. So that's what they do. Now there are applications where people will run, they'll take more time to actually work out a better permutation because they're going to use this a gazillion times. Okay, so this would be the case for embedded systems, like for control, right? So if you're doing control and you're going to put this into, let's say, a rocket or something like that, and it's going to run at 100 hertz for like the entire mission or whatever it is, right? That's a lot of time. It's worth, you could definitely take an evening to come up with a better permutation. But this is not what most people doing most people doing numerical who work on the solution of sparse linear equations don't do that. They just stick with heuristics that are fast. So, and by the way, that portion is called the symbolic. Sometimes they call that the symbolic solve, or the permutation phase. There's lots of names for it, right? And you can tell if you actually, if you do things like, if you actually look at it to see what it's actually doing, you will find out that it's spending a whole bunch of time and it's doing graph calculations. There's no floating point numbers involved. Okay. Then when floating point number operations start up, that means you're actually doing the numerical factorization. So that's a good question. Okay. So now I know I'm not able to, I mean, I realize for many of you, if this is the first time you've seen it, that's fine. You should just get the high level picture of it. And you could read this a little bit more in the appendix in the book. There's an appendix on this. And this is just something you should know about. So I don't know, SciPy, you could poke around in SciPy or something. Once you know about this, you can't unknow about it. And it's kind of, you will have like incredible powers. Yes?
What kind of heuristics?
Well, they do. So some are kind of greedy. I'd have to tell you actually how you actually do the factorization to actually explain the heuristics. But a lot of them are just constructed one by one. What they do is they say P is going to permute something to the top row, and they'd say I'm going to find which entry I should permute to the top. Then who gets permuted to the second top, then third top and fourth top, things like that. So it's but that's greedy. But that's the kind of things people use. And they have lots of names, and it's worth knowing a little bit about them. Yeah?
So it doesn't be hard for finding the best one, but are there like approximation guarantees?
No, there's no approximation guarantees whatsoever. None. Right. So, yeah, no one has. Yeah. So, yeah, I know it's one of those things where, we can ask, of course, these are all graph calculations. It has nothing to, these are just questions about graphs, right? Oh, there is one exception. There's one theory of it. That's this. If the graph represented by the sparsity pattern of A is chordal, then it turns out there is a it's guaranteed there exists a permutation which has zero fill-in, meaning the number of non-zeros in L will be identical to the number of non-zeros in A divided by 2. Right? So that, if you know what a chordal graph is, that's one of them. That's actually kind of useless, frankly, in practice, because the real question is not whether there exists one. The question is whether our heuristics find it. And the answer is all decent heuristics will find that one. So, yeah.
Each of these factorizations have required that we know the matrix is non-singular, or that it's positive definite.
No, so it turns out most of so in this one, to find the permutation for Cholesky factorization, you actually don't have to know the entries in A. You simply have to know their locations. That's actually a super important, more advanced, but you brought it up. So what this means is we can do this ahead of time. So for example, if we're solving an optimal control problem or something like that, we can do the permutation once and for all offline. And then when this thing is actually running a jet engine or something like that, then we don't have to do it. If we're doing finance and we want to do an insanely fast back test, right? We would first we'd first do the factorization, and then after that, every solve is going to be really fast. So that's how that works. Yeah. So you don't have to know. If A is not positive definite and you call a Cholesky factorization on it, it will fail at some point. At some point, it's going to attempt to take the square root of a negative number, right? And then it'll throw an exception to you of some kind, right? But that's the only time you would ever know. Yeah.
I'm just curious, when does the solver know stop? Like, what kind of criterion?
Oh, sorry. All of these are finite algorithms, right? And in infinite precision, they just solve, right? I mean, when I say it's order n cubed, it means I can tell you for this, you're going to do, 1 billion, blah, 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 multiplies, 1.3 billion adds. When it's done, if you did everything in infinite precision, you would have the answer. End of story. There's no stopping criterion. There's nothing like that. Yeah. Now, of course, you're doing this in finite precision, right? So since you asked, there are methods to do something. It's called iterative refinement. And what that does is you compute a solution that's approximate, and then you can iterate to get a better solution. And people know about that, but that's a little bit beyond what we're talking about here. But it's good to know about too. Okay. So LDL transpose factorization, this is any non-singular symmetric matrix, right? By the way, we'll see examples of where these come up, like maybe next week, in fact. So here, it's like L, it's like an LDL transpose factorization, but D is diagonal, and it's either 1 by 1 or 2 by 2 blocks. So that's just a mathematical fact that you might need to have these 2 by 2 blocks. But the point is, those are all easily inverted matrices. Permutations, yes. Lower triangular, yes. A block diagonal matrix with 1 by 1 and 2 by 2 blocks, I think we know how to invert that. That one we actually literally know how to invert, but we can certainly solve equations like that, right? So, okay. So this is the LDL transpose factorization. And now we're going to talk about something. This is something probably many of you have seen in other contexts. It comes up in pretty much all fields. So it's something called the Schur complement is the name of it. And I think you've already seen it in early on in the class or something like that. But I can't think of a legitimate field where it doesn't come up, right? So in statistics, it's conditioning a Gaussian on some entries, right? In mechanics, it's actually what happens when you impose the boundary conditions on something and ask where everything else is. In electrical engineering, you take a network and I put a termination on some of the ports on the network and I ask what's happening with the rest of them, right? So all fields have this. Okay, and the idea is actually embarrassingly simple. So it goes like this. We're going to write AX equals B. We're going to block A into some blocks like A11, and I'm going to have A11 and A22B squared, right? And I'll also conformally block X and B. So they're going to be called X1 stacked on X2 and B1 stacked on B2, right? Okay, but nothing has happened. I just decided to name it this way. So I just divided it in some weird way. Okay, what happens now is you do kind of what you learned in maybe high school, except those were numbers and not matrices. And so what you do is we just work out, we can actually just solve this in a weird way. So the first equation, block equation, is A11 X1 plus A12 X2 equals B1, right? And we're going to assume here, we're going to make an assumption that A11 is invertible, okay? Then, so what that says is, well, I could do this. This is minus A12 X2, right? That's that, right? And then I'll just put an A11 inverse here. Okay, so there we go, like that. Okay. Yeah, by the way, already when you see this is hinting that this is going to be interesting when A11 is easy to invert. So that's going to be the interesting part. Okay, but we'll get there. Okay, I plug this into the second equation, and the second equation is like A21 X1 plus A22 X2 equals B2. And I plug this expression in here, and I'm going to get something like, A21, A11 inverse times B1 minus A12 X2 plus A22 X2 equals B2, right? So makes sense, okay? And then I rearrange that to look like this equation here, right? I just put, and that's another equation in X2. This matrix here is famous, and it's called the Schur complement of the original matrix. I can't remember if it's with respect to the 1,1 or 2,2 block, but it's one of those two, and I don't remember which it is. It doesn't matter. It's a Schur complement, okay? And you've probably seen it before or something in some, yeah, anyway, that's it. Okay. Okay. So you could use these calculations to solve the original thing. And that generic algorithm looks like this. It says first you should form A11 inverse A12. Because that's this thing, right? And A11 inverse B1, right? Oh, by the way, so let's talk about how we would do that. So the way you would do that is you'd factor A11, okay? To compute this, you would do a solve, right? Because you've factored it and now you do a solve. To calculate this, you do a solve on each column of A12. Everybody got that? Right. So this could be, that could end up being that's quite efficient, right? So the way, this, if I were to double click on that and expand it, it would look like this. Factor A11, then solve with B1 and solve with each column of A12, right? That gives me these two matrices, okay? Next step is I form S, that's the Schur complement, which is this thing. And I form this B tilde thing over here, which is the right-hand side of this equation, right? So this equation up here is Sx2 equals B tilde. And then what I do is I find X, what here is I do a factor on S, then a back solve, and then I can reassemble. This gives me X2 directly, and I can get X1 from like this equation here. And by the way, when I solve this equation, I already factored A11. So this is a solve, okay? Right? So this is okay. So that's the idea. Now, okay, now's a drum roll to find out, is this faster? Is it better? And it's actually kind of interesting. So if in step 1, you have F is going to be the factor cost for A11, S is the solve cost. So in the first case, you factor A11 once, and then you solve for all the columns of A12, and so that's N2. S. So that's the cost of step 1. Step 2, and here that's actually just forming the Schur complement matrix. And what we're going to do is we're going to imagine that that the Schur, we're not going to exploit any structure in the Schur complement, although one could, but we're not going to. We're just going to treat it as dense. And then step 3 is going to be N2 cubed, because it's just to factor and solve it. Okay. And so the total is this number up here. It's F plus N2S plus blah, blah, blah. Okay. All right. So let's just throw in a general A11 and see what happens. When you do, I mean, hardly surprising, but actually down to the flop, it's identical. And you've done congratulations, you've done a bunch of algebra and analysis, and it did absolutely nothing. Okay? So everybody got, oh, by the way, it does nothing in terms of flop count. In reality, it does do things, right? So in fact, people use this sort of block elimination method. They actually use these for dense matrices. And the reason is you would choose N1 and N2 so that one of these solve methods could be done at some level of cache, right? And therefore done quickly. So that actually happens. But again, all of us are blissfully unaware of those details. Okay. Now it gets interesting. It's interesting precisely when F is small compared to N1 cubed. So I'm going to give you, here's a great example, is diagonal. So what the factor cost for a diagonal is 0. I mean, whatever, or N if you want to, whatever, it doesn't matter. No, it's here. L is going to be the matrix itself, and U will be the identity. There, it's 0, okay? But so here, it's actually really interesting. You get 2N2 squared N1, right? Plus 2/3 N cubed. What's amazing about that is that's linear in N1. So now I'm going to show you some I'll show you some sparsity patterns. And here it is one. Actually, I was just showing you one. I had one right there. Here's one. Remember this one? That's this downward arrow pattern. Someone suggest a blocking of it. Like, what would be A11? Do you see a leading matrix here that is easy to invert?
Diagonal.
Yeah. So here's A11. It looks like this, right? Right? It just looks like that, right? So this is A11. Diagonal, actually I was going to say matrices don't come easier to invert than diagonal. That's false. Here's one that's easier, is a multiple of the identity. That's pretty straightforward. Actually, I think in terms of flops, it's the same anyway, so it doesn't even matter. But anyway, here it is. Okay, so here's one where instead of this, so N1 is, I don't know, let's suppose the original thing was N. It's N minus 1, and N2 is 1, because this thing is 1 by 1, right? Down here. And so in this case, it turns out you're going to get a stunning reduction, right? Because you're going to be able to, you can invert this fast. And in that case, you would get exactly this number over here. You would get, 2 N2 squared N1, right? So, okay. That's one example, but I'll show you some others, right? What it means is, if you saw, what if you saw a sparsity pattern that looked like this, right? This is banded, and then over here, these are like dense. This is called dense rows and columns. Everybody got that? So actually, it's just a block arrow matrix, but with a thicker weight on the things because they're wide, right? That's banded, and then this is a whole chunk of stuff over here, right? Everybody got that? So what this says is that this block elimination method here will solve that. Well, it's actually insane. It's actually going to be linear in the dimension. If this doesn't grow this way, and if the bandwidth doesn't change, this gets bigger and bigger, and we can solve it, right? So anyway, it's pretty cool, right? So and that means if you see that, you should smile. We'll put it that way. Or you're not going to see that, probably, because someone would already have to know. But the way it's really going to work is someone's going to be talking about a problem. It's going to be some weird, complicated problem. Who knows what field? It doesn't matter. They're going to be talking about some complicated thing. While they're talking, you will be forming in your mind what the sparsity pattern of the associated matrices look like. Okay? When that image comes to mind, you will smile. And you will say, I can solve that problem in half a second. And they said, I can't even load it into memory. And you'd say, just chill, and I'll show you what we're going to do, right? Everybody following this? So I mean, these are incredibly useful things, right? So, and we can think about what this is. This is basically a set of equations where banded means that equation, 50 only references, let's say, variables 40 to 60, okay? And that would be here. Then you say, but there's some special variables here which affect everybody, okay? So that's what this is. So you're going to want to be making those, to be fully developed, I would say here's what you want. You want to be able to get a feel for when applications involve matrices that look like that. Then you're going to be happy because you're going to know something other people in the room don't, because you're going to know that you can solve that in linear time, right? So that's why people will say, like, well, I have to find this whole trajectory. It's like, it's 100,000 time points, and you're like, so, but do you have a phone or whatever? It's just not going to be that complicated, right? Again, if you know what you're doing, okay? So, okay. Okay, so now this leads us to, and this probably people have seen. It's got lots of names. It depends on where you're from. I think it's called like Sherman, Morrison, Woodbury. Sometimes it's called the Woodbury thing. Sometimes it's called the matrix inversion lemma. And I have a friend who can actually tell where someone learned their linear algebra because they use different terms. They even use different terms, I believe, at Oxford and Cambridge, just so you know. So this is like someone can, just by asking someone what they call this, and a couple of other questions, you can figure out that they got their PhD at Oxford or Cambridge or something, or Harvard or whatever, anyway, or MIT or something. Okay, so here it is. You start with A plus BC times X equals B, right? So and in fact, some people call this a low rank perturbation of A. I mean, that's not fair because no one said that B and C are small, right? But if B had small columns, if B had just a handful of columns and C had a handful of rows, this would indeed be a low, what people would call low rank update to A, okay? So we want to solve a matrix that looks like that. So, and in fact, an extreme case would be things like, here's one you hear all the time, diagonal plus low rank. There, A is diagonal and B and C are small, right? So B has got, a small number of columns, C has got a small number of rows. That's super common. That's also something you will, I would hope, never ever forget. Diagonal plus low rank. And it's all related. Here's how it's related. Actually, let's just talk about this in the case where A was diagonal and B and C have modest number of columns, right? So in fact, here's one. So basically all of quantitative finance uses a risk model where the covariance matrix is diagonal plus low rank. And it's called a factor model, right? So there, C is B transpose. And if this were like a Gaussian or something, if this is the covariance of a Gaussian, if you understand what I'm saying, that's fine. If you don't, that's also cool. But this is just completely universal, right? So you'd have what it would mean is it's even got a Bayesian model, and it basically says that the returns of all these assets is driven by, let's say, B and C. They typically B is about a width of 100. That would be very typical. C would have a height, C is B transpose, right? So you'd say, look, I don't know what these 8,000 returns are doing, but they're mostly driven by these 100 factors, right? Which are actually, so that's the underlying, that's what's actually driving the returns. And then the A is diagonal, and they have a beautiful name for it. It's called idiosyncratic. So that's the idiosyncratic risk. It's the amount by which, Google or, whatever, Coca-Cola or whatever it is, Chevron goes up and down. It's the part, in fact, the way they would say it, this is dialect, is you'd say, that is the part of the variance not explained by the factors. Everyone got that? So that's it. So, and the factors are actually kind of interesting. Sorry, this is just a weird aside, but since we're here, I'll just continue. The factors are interesting. Some are handcrafted. So they're literally matrices with zeros and ones and weird stuff like that in it. Like, what region are you in, right? Are you a pharmaceuticals company? Are you do defense? Do you do that kind of thing? Others are actually crafted by, people using numerical algorithms. So, okay, that was just a small story about this. Okay. If I have something that looks like that A is diagonal and B and C are small, I can store that, like no problem, right? That's even for very big. Like if you want to run a fund that is looking at a universe, I'm using dialect, of let's say 100,000 assets, right, across the whole world. That I know people who do that. But so you do that. So the covariance matrix is 100,000 by 100,000 matrix. For something like that, someone say, well, yeah, what's your risk model? And they would say, oh, I have a 200 factor model. And that means their covariance matrix is expressed as a diagonal matrix, right, which is whatever it is, 100,000 by 100,000. And then they have 200 factors. And all of that is completely storable and stuff like that. And you'll see, in fact, not only can you store, you can actually solve problems super fast and things like that. Okay, all right. That was all a weird aside, but let's keep going. So now what you do here is something that is actually a little bit unintuitive. It's called you uneliminate. We did this before in duality, and it turned out well there. What you do, to uneliminate means to introduce new variables, right? Right, to eliminate variables means to, solve for them, get rid of them, and then substitute back their values into the rest. That's elimination, right? That sounds good, especially to an amateur or somebody first seeing this material because, what are you doing? You say, I'm eliminating some variables. Why? Because I like to solve smaller sets of equations. Everyone, it makes perfect sense, right? It's completely and totally wrong. That's not how you should be doing linear algebra, but it does sound good and people can fall for that, right? Okay, unelimination is the opposite. You say, thank you for your set of equations. If you don't mind, I'm going to introduce new variables and equations and make it a bigger one. And someone's like, what? Why would you do that? Everyone see what I'm saying? You'd say, thank you for your 1,000 by 1,000 set of equations. If you don't mind, I'm going to expand it to a 10,000 by 10,000 set of equations, if it's okay with you, right? And they would say why? Anyway, and the answer is, you'll see why in a minute, right? So we write this way. We just introduce a new variable, which is y, which is cx, right? So, and I write that second equation as this bottom row, which is cx minus y equals 0, right? So the second system of equations is bigger, and it is completely equivalent to the first one, right? Okay, now let's talk about this. When you see a matrix like that, you just encountered all this so far just a few minutes ago, so I don't expect you to have this response now. But hopefully within a week or two, you should have the following response. You will see a block there, a minus I, and your eye will go to it because it's really easily inverted. and you're going to see a block, and you're going to say, well, you're going to have an urge to do block elimination on this, right? Because that, and so what you would do is you'd say, oh, I know what I'm going to do. I'm going to permute the minus I up to the top, and then I'm going to use block elimination from the previous stuff, right? Everybody got that? And then you eliminate it, and you'll end up then forming the Schur complement equations, and it will be a plus bc x equals b. So you'll be right back where you started. Okay, so here's what you do instead. You resist the urge here to eliminate the minus I, even though it is a very attractive target for elimination because it's easily inverted, right? You resist that urge, and instead you eliminate A. And you will end up with a Schur complement equation that looks like this. Okay, and this allows you to get y. Here you solve for y, then from that you plug it back in and get x, and you end up with a formula that's called the matrix inversion lemma. That's the neutral version. It says that a plus bc inverse is this horrible formula over here. Yeah, so that's it. This gets interesting if like a is diagonal or something like that. Then anyway, a lot of things would come out of that. So how many people have seen like matrix inversion lemma or something before, or some Sherman, Morrison, Woodbury? It's the same. Okay. Any other names for it? I used to know at least one or two others, but anyway, anybody else know another name for that? It's a thing in linear algebra, and how you call it depends on where you came from. So, okay. Okay, so I think actually well, here's an example. Like A diagonal and B and C are dense. This is, you basically form, you're going to form D is A plus BC. This is if you do it the dumb way, right? You just write it out as a dense matrix, then solve. In this case, then you get something that's Pn squared, n cubed. And if you do it the right way, you get something that's linear in n, right? And these make a big difference, right? So, yeah, by the way, a lot of this stuff subsumes things that were taught in the 60s, 70s, and 80s. And sometimes in the 90s by people who learned it from people who learned it in the 60s and 70s. Okay, so for example, if you teach a course on control, you might, I've done this, I haven't done it for a long time, I won't do it again, but you go through a long derivation of what like the Kalman filter is, or how to solve an optimal control problem, right? And it's very clever, and you have little parts in this Bellman equation and blah, 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 and you end up with stuff that actually works. It's great. A very funny thing happens. If you simply take the problem represented by an optimal control problem or a Kalman filter and just throw it at a sparse solver, guess what? It'll be just as, it'll do it. So basically all of those lectures were useless, is what I'm saying, as a practical matter, which is kind of embarrassing, but whatever. So I don't teach that anymore. So I don't teach it that way anymore. I just say you get a giant set of linear equations and you solve it using sparse methods. Done. That is the correct way to do it. It gives you a lot of stuff, right? So this is in a lot of fields. Like, yeah, I think I'm almost certain in statistics there'd be many, many papers written on if you had a factor model. So that's a covariance matrix is diagonal plus low rank. And it would be all sorts of things about very intensely clever ways. I could condition, suppose I gave you 80% of the entries of a vector, and I said, please compute the conditional means of the remaining ones. Everybody follow this? That's like a conditional mean imputation task, right? So I'm sure there's whole papers written on this and clever methods for doing this and blah. Anyway, the answer is you form the covariance matrix, literally write down the equations you want to solve, and then you do nothing but pass it to a sparse solver. And it'll be just as fancy, probably more general than all those papers. So, okay, it's embarrassing, but true. So okay. All right. So I'm not going to go into this. There's a whole lot more I haven't told you about linear algebra, but these are the main points. So, okay, so let me, right now this is just sort of hanging here. Now you just know about linear algebra, but I promise in the next week, we're going to connect it to problems and then to optimization problems, and that will have a connection to applications. And then you will start being able to listen to a problem a practical problem and say, I can solve that. Like I can solve that super fast, right? So everybody getting this, right? So I mean, there's people where this is all they do, right? If you do scientific computation, this is kind of a lot of the stuff you do. So, okay. So now we're going to start unconstrained minimization. And we'll, like I say, we're building slowly up at the lowest level. Well, at the lowest level are, computers, compilers, microcode, things like that, which we're not going to look at. Next level up, the bottom floor is what we just covered, was linear algebra. Now, the next floor is how do you solve smooth, unconstrained problems. So we'll look at that first. And we'll build slowly up. Then we'll get equality constraints. Then we'll pull in inequality constraints, and then we're there, right? So, okay. So here's what it looks like. We're going to minimize a function f here that is, we're going to assume it's smooth and twice continuously differentiable, right? And we'll assume that the optimal value is achieved, right? So there's at least an optimal point, right? Now, by the way, a lot of problems like that we want to solve in this class, problems you have already solved, don't satisfy this, right? Like if you did an L1 fitting problem, you would minimize the L1 norm of AX minus B, and that doesn't count. That's not here because that's not differentiable. Okay. Okay. So this is what we're going to do. In general, except for a very important set of problems we will see shortly, there are no analytical solutions to this, right? Instead, we're going to have iterative methods. And an iterative method is going to generate an X. It's going to query something about F and then generate a new X and so on, a new X and a new X. And what's going to happen is those X's are going to converge to, hopefully a solution of this problem, right? And what we'll do is, the typical thing you're going to get is something like this sequence is going to have the function values converge to the optimal value. And another way to say it is that the gradient is you're going to have a sequence of points where the gradient gets smaller and smaller. Okay? And then when you deem it to be small enough, you asked earlier about stopping criteria. Here you have stopping criteria. For the direct methods, you don't have stopping criteria. Well, it just stops. It's like after n cubed over 3 steps, you've got the Cholesky factor. There is no stopping criterion. Here there is. Okay. So we'll make some assumptions. I don't want to get too technical about it because it quickly gets kind of boring and stuff like that. And by the way, there's entire classes that cover nothing but this material in hideous, full mathematical detail. So I mean, they're interesting, but I don't know. I think then some people grow out of it or so. Anyway, I'll stop here since that's fine. Okay. So yeah, we're going to assume that the sub-level sets are closed. And one condition for that is pretty common, is that the function f is closed. Like if you do convex analysis, which is the mathematics of convex optimization and convexity, this is a central concept. It just means that the epigraph is closed, right? And one example would be if you had here's some examples of some closed functions, right? Log sum x. This is because the domain of this is anything, right? So this would count here. Here's another one. This is weird because you might say, but there's a constraint. The constraint is that x lies in the interior of this polyhedron, because otherwise, I mean, there's an embedded constraint here, and you might say, no, I don't like that. But this one is perfectly good. All the sub-level sets are closed, and that the reason is that the function value goes to infinity as you approach the boundary. So we'll get to that. Okay, is that okay? So these are technical conditions. I think not super duper important. People are sometimes assume something like a minimum curvature, right? So what that says is, for example, the minimum eigenvalue of the Hessian is bigger than some number m, which is positive, right? That gives you a minimum curvature to the function, right? That'll allow you to say all sorts of things. Yeah, now you could ask questions like, how would you know what the minimum curvature is? Like, it's a good question, right? And the answer is, in most cases, you would have absolutely no idea. There are cases where you do. Here's one. If I do, let's say I do multinomial logistic regression, and I add quadratic regularization to it. Then I don't even count the curvature that comes from the multinomial logistic regression loss. And just the quadratic regularization alone gives me a minimum curvature. Everybody follow me? So, I mean, but these are kind of rare, right? But that is an example where you actually would know a candidate value for M, right? Which is literally the, it's going to be the regularization, the ridge regression, parameter. Okay, so if this is the case, then this says that F minus M times the norm of, x squared is actually convex. And if you apply that, if you then apply the basic convexity formula to that, you'll find out a really cool, you get a strengthened Jensen, I guess it's not Jensen, whatever. This first part, this up to here, that's true. This is true for any convex function, this part, right? That's the basic inequality. What this says is, oh yeah, well, it applies with a little bit more, right? It's actually, that's the minimum curvature constraint, right? So it strengthens that basic inequality we saw 6 weeks ago, or whenever it was, 7 weeks ago, 6, right? Okay, and this means all sorts of cool things because, for example, I could minimize both of these equations over y. On the left, I get p star because it's just the minimum f of y. On the right, this is a quadratic function in y. I set the gradient equal to 0, I minimize it, and you get a number which is actually, it's going to be, anyway, you end up with something that looks like this. You end up with this inequality, right? And so this is kind of cool because this says that if you wanted a stopping criterion, you would run the algorithm, you'd evaluate the gradient, and when the gradient gets small enough, you quit. And someone says, why are you quitting? And you'd say, well, the gradient is less than something. And they go, yeah, but how far am I from optimal? And then you would say, oh, good question. I can actually bound it. I can say that here's how far you are from the optimal value, no more than 1 over 2m times this. Of course, then in general, someone would say, how do you know m? And the answer is you don't, and blah, blah, blah. So, but okay, everybody. But this is the justification you would have for stopping when the gradient is small. Okay. So we'll say a little bit about descent methods. These are, these are super widely used. And they all have there's a generic form, and it looks like this. In each step of a descent method, you're going to find something called delta x, and that's called the step or the search direction here. And so, basically what happens is at iteration k, you have xk, you make some queries to f about like what's the gradient or something like that. And then you form this search direction. So you stop and you ask for directions, and it says, well, you're here, you want to minimize, you should kind of go that direct. That's delta x, that's this direction. Then what you do is you're going to go in that direction, but with an amount that you're going to then choose. And that amount is scaled by this factor t, which is positive. And this is, that's called sometimes the step size or the step length, even though it need not be, it's not really the length unless the norm of the gradient is equal to 1. Right? But still people call it the step length or the step size or something like that. So, okay, that's what you do. And it turns out if the direction you move in has a negative inner product with the gradient, then it turns out, and if you choose the step size correctly, the new point will actually have a function value less than the original point. That's good. That's called the descent method because you're kind of descending. Right, and you end up with a function value that's lower. Okay, so here's like a generic version of it. To make this a real algorithm, we have to fill in things. We have to figure out how do you find the descent direction, and then we have to figure out how do you choose the step length, right? And that's the whole thing, right? And the stopping criterion could be some norm of the gradient. Usually it's not. Usually it's something that is computed as a byproduct of these two steps in here. So this is going to be like hundreds of different methods with different names are going to have exactly this form, right? And they differ in what's the search direction, and they differ in what is the line search. Okay, so that's the idea. So for line searches, there's a bunch. I mean, here's one. One is an exact line search. That says once you've decided that you're here and you're going in that direction, you actually look at the function restricted to that ray. And then you look for the point where along that ray you have the smallest value. So that's called an exact line search. And you could do this in some cases, right, where you can actually work this out analytically, or you can compute it cheaply or something like that, right? So that's one place where you might do this, right? Another one, which sounds much cruder, is called a backtracking line search. And this has many, many names, again, depending on where you came from. It's called an Armijo line search. It's got all sorts of names for it. In Armijo condition, there's at least one of those. I forget what it is in Russian, but they have a different name for it. So it's all this. There are lots of different names for this. So this has been rediscovered, like, I don't know, a couple hundred times. Here's the way it works. It's called backtracking, and it goes like this. You start with t equals 1. So you try x plus delta x. Then what you're going to do is you're going to check whether f has gone down, and this is critical, enough. By the way, if it went up, that's really bad, right? In fact, you can even be out of domain. So that would be like a very, that would be it went up a lot because it went up to plus infinity, right? So, okay, so here's what this looks like. Here's t here. Here is the function restricted to t. This would be the exact line search number. That's the exact step length you would take. You'd take this to minimize this, right? So the way this works is you look at this basic inequality here. That basic inequality is this line right here, right? This dashed line. That's and what it says is, if I put alpha equals 1 in that equation, I can reverse that inequality. Because basically when I continue this linear thing, I guarantee this is a lower bound on this, right? So the actual function value could never be below this if the function's convex, right? So here's what you do. We put an alpha in there, which is a number that's less than 1. Actually, in fact, it's less than a half for weird reasons. It turns out it's not going to matter what it is too much. And then we degrade the slope by multiplying by alpha. So here alpha is maybe a third. I just made it up. And that would be this line. So if you take a really small step length, you're definitely below this line, because if you take a really small step length here, this is actually a really good approximation of how much the function is going to go down, right? And then the rule is you have to be below this dashed line, this degraded predicted line. And so what that works is, you might start here and query the function and find this value, and you're above this. In fact, the most dramatic one is you'd start way out here and you're over here. And actually, when you do x plus delta x in that case, you actually have a higher value than f of x. Everybody see that? So that would be a particularly poor choice of step length, right? So what you do then is you multiply this by some factor beta. Beta is typically like a half. People use that. They use 0.1. So you simply say, okay, that was too much. So you go back by half and you land here. You try this one, you get this value. It's less than this thing, and you accept it. So you take the first one, you accept. That's backtracking. It looks, now, your intuition, actually the story of a lot of this unconstrained minimization is that I guess there'll be several times when something you would think is right is just wrong, completely wrong. So now I'll tell you the first one. You would look at this and you'd say, it's obviously, clearly it's better to do an exact line search. That's totally obvious, right? Because you're actually minimizing the function along this line, right? This makes sense. And this crude thing that stops when you've gotten like some acceptable, by the way, people use numbers like alpha equals 0.01, right? Meaning if you get even just the slightest decrease, like good, fine, thanks, we'll take it. So everybody see what I'm saying? So looks very unsophisticated, right? Anyway, all right, now I'll tell you the punchline. The punchline is it doesn't make any difference. That, in fact, exact line search is not only not better in practice, it's often worse. And the simple dumb thing actually works just fine, thank you. Right? This is not obvious, right? So, okay. Now we get to a gradient descent method. This is the simplest one. Remember, we had to choose a direction. I mean, I would hope it would be the first, it should be the first thing you would think of. Someone says, make me an iterative method. I'm at f, I'm at x, and I evaluate f at that point, and I evaluate a gradient. Now, gradient is pointing in the direction of fastest increase of f. If I move in that direction, f goes up as fast as possible. If I move in the negative gradient descent direction, f goes down as quickly as possible. And you not only would you come up with this, but you'd also ask yourself, why would you do anything else? I mean, you realize think about if you didn't do the gradient method, what happens is you arrive here and someone says, where's the negative gradient? You go, that direction. You'd say, well, what does that mean? You go, if you go in that direction, you're going to go down as quickly as possible. And you go, cool. Which way do you recommend I go? And you go, that way. You're like what? Like, why would you recommend that? Anyway, you will shortly see why, but it's kind of non-intuitive, right? But we'll get to it. Anyway, so gradient method is the most intuitive one. It looks like this. It doesn't matter what line search you use. And here it is. And you can, prove convergence of this and all that kind of stuff. That's fine. It turns out this is often unbelievably slow. So in fact, we'll see what other search directions can actually dramatically improve this, but this is slow. Very weird. And we'll look at a picture to understand it. So I just take a quadratic, looks like this, right? And here's some level curves of the quadratic down here. And gamma is a number. Let's see. So gamma allows me to change the eccentricity of the level sets, right? So if gamma equals 1, this is 1/2 x1 squared plus x2 squared. Oh yeah, by the way, what's the gradient in that case? So the level sets are just circles. You're here. What does the gradient look like? What is the gradient? It just, in that case, this is actually more, I'll draw this even, it's fine. Here. So here's your function. Here are the level sets. Here's 0, right? These are level sets. You're here. The gradient points directly out like that, and the negative gradient points directly towards 0, which is the minimizer. So if gamma was 1, if I asked you to minimize x1 squared plus x2 squared using the gradient method with an exact line search, tell me about how well that algorithm is going to work. Yeah, very well. Like in one step, right? It's going to say, which way should I go? You say steepest descent, which just happens in this case to aim directly at the solution, right? Then you do an exact line search and it's game over. Everybody got that? Okay. So, but now, that makes sense. And in fact, someone who was proposing a gradient method would say, yeah, look how well that works. That's great. Like, why would you not do that? Why would you go in a crazy direction like that, right? But we can actually control the eccentricity by making gamma either really big or really small. And in this case, you can actually work out analytically what the iterates are, right? And you get something that looks like this. It's actually a very good picture to have in your mind. Of course, it's totally silly because we don't care about two-dimensional problems. We care about problems with a minimum dimension of 200, 2,000, 20,000, 2 million. But nevertheless, this gives you the picture. So here, this is when it's just slightly eccentric. And here, these are the level curves. And so the negative gradient is just simply, the gradient is these are orthogonal to the level curves. And it says go in that direction. This is the minimum, because we're doing exact line search. And then it says, which way should I go? And you go like that. Everybody? So this has got, people refer to this as zigzagging. We can make it arbitrarily bad, right? We can take gamma equals 1,000, and you'll find out that this thing's basically going like this. And I think there's even a name in Western optimization. It's called the Muratos effect. Right. So, but it's just, the other thing I like is it's just called zigzagging. Everybody got this? So, by the way, when you see this picture, you can kind of figure out some things immediately that would be pretty good, right? So if you're in EE or any other field, you would say you're kind of going in the right direction on average, right? I mean, the problem is you're just doing this weird thermal thing up and down like this, whereas you want to really kind of be going that way. And so you'd say, you know what? You should run those search directions through a low-pass filter or something. I mean, again, I'm speaking dialect. Or if you do physics, you'd say, Yeah, add some momentum to it or something like that. Or viscosity, add a viscosity term, right? So that you would then you do something that would go right like that and head towards the solution, right? So, and those are all methods. We're not going to look at those, but that's kind of the idea. Okay, so even this baby example tells us that, but we get some really good intuition here. The gradient method works really well when the sublevel sets of your function have low condition number, or they are round. Because if they're round, the negative gradient points directly to the solution and you're going to go there quickly. If it has high condition number, or if the sublevel sets are weirdly squished out like this, that kind of thing is going to happen. Everybody got that? So that's kind of the picture here. I mean, that's actually super important observation because we're going to use that. That's actually the segue to basically Thursday's topic, right? So, okay. All right. So here's just some examples. This is a silly function. It's non-quadratic. And this happens if you use like a backtracking line search. And here's an exact line search. And you'd look at these two and you'd go like, well, I told you exact line search was way better. But this just shows you kind of the idea. But it shows you that in real real examples, you're actually getting this Moratos or zigzagging effect, right? And then we can look at that over here and see what that looks like. So this looks like this, right? And let me explain what this is. These are the iterations, right? This is a log scale telling you actually your suboptimality, right? And what you can see is all sorts of weird things here, right? Like the first thing is that actually between 0 and like 100 iterations, for whatever reason, the backtracking line search was doing better. Like, I don't know why, but it was. And this is kind of common, right? So this is what it looks like. The other thing you see is that this kind of gets kind of linear, and that's referred to as linear convergence. But that's a weird use of linear because it's linear on a log or a semi-log plot, right? So it means, because this is a log thing, what linear convergence here means is that each step you do, each iteration, reduces the error by some factor. It's pretty small, frankly, but we could work out what it is, right? If you divided it by, well, let's just say that hit here. So let's to go from 1 to 10 to the minus 4, that took you 170 iterations, right? Then that tells you take 10 to the 4 and you take that to the 1/175th power, and that tells you how much your error gets smaller each step, right? So that tells you roughly what it is, right? Okay, so that's called linear convergence. Okay, I think maybe what we'll do is I won't even start the next section, but this is a good place to stop, and we'll continue next time.